I wanted to talk a little bit about your first homework problem for Monday. This is the Putty hits the rotating rod problem. It involves a rod that is initially at rest. Looks something like this. And it has a length of L, like so. And there is a ball of putty that is thrown towards this rod, and what happens is that the ball hits the rod and sticks to the rod, and then the rod and the ball of putty move together. I think there was a number of questions on this problem, so we can look and decide, well, what are we going to likely need to use to solve this problem? Well, this is in the chapter on angular momentum, so that's a bit of a hint, but we also want to make sure that something is going to apply, right? We have a ball, it has some particular velocity, it's coming in, it has some mass, it's going to hit this particular rod at this point out here, and then it sticks to it. So, like we talked about before, a lot of times we think about angular momentum as being being some type of like rotating disc or a sphere or a cylinder, but we can also describe the angular momentum of a single particle. So for an instance, in this case, we know that the ball is going to, we know that the object, the ball and the rod, are going to be rotating about this point of axis. It tells us it's fixed in the middle. And so when we consider the ball at this point is a little bit maybe too far, but if we consider the ball, it tells us the speed of the ball just before it's about to hit, right? So we can draw it right next to it and just say it hasn't actually hit the rod yet at that point. And it actually tells us what the velocity vector then is at that point. And the velocity vector might be equal to some quantity. Mine's going to be different than yours, so that's not going to really be all that helpful. But at that point, it has some mass and it has some velocity. And so that means it has a momentum, right? Because the momentum is equal to m times v. And it has some angular momentum about this point of rotation, which is defined by r, whatever r is at that point. And just before it's about to strike this, that value of r is equal to basically the exterior point. Like the way it draws it in the picture is actually a little bit better. See, I drew my ball kind of a little bit towards the middle. The picture on your lawn kappa makes it kind of clear that it's pointing directly towards this outer edge. So we assume that the lever arm, the angular momentum of this ball, just before it strikes the rod, is actually going to be equal to the lever arm, the displacement from the point of axis, the point of interest really, which is the axis of rotation of the rod, and that with the cross product of its momentum vector, right, which is defined by the direction of its velocity. So this is the initial momentum in the system. The rod isn't moving, but we have this ball is going to impact this tip right here. All right. Then after it starts to move, we have to consider, so this is the initial momentum, and the final momentum is going to, we're no longer worrying about this single piece of stuff, right? We actually have the, we could do this a couple of different ways, I guess. What you could consider is what its angular momentum is going to be. So let's actually chop it up, right? We have the angular momentum of the rod, which is going to be equal to its moment of inertia of the rod times its angular velocity of the rod, plus, so that's one piece of it, the rod moving, plus you have the ball, right? So you have the moment of inertia of this ball that's stuck to the rod times its angular velocity. Well, since they're stuck together, the angular velocities here are going to be the same, and we need to make sure that we consider which of these moment of inertias is correct, right? You should be able to look up the moment of inertia of a rod rotating about the center. The ball, it's maybe a little bit more confusing, but for a ball that is in a single mass in rotation, it's the same equation you would use for a hollowed out cylinder, and that is simply m times r squared. N times r squared. One problem that I had in doing this problem, where the L here, I guess I'll just tell you what this is. So this is 1/2 m of the rod, this is the ball, times L squared. Now the reason this is L is because it tells us the length of the rod is L. Not to be confused with L being the final momentum. Okay, this is L meaning the length of the rod. So even though this is rotating about its center point, the calculation, the equation we use to calculate that is equal to the 1/12 the mass of the rod times its length, its full length, not from the axis of rotation to the edge, but its full length squared. That's different than the moment of inertia of a single ball or a spherical shell, because in that case we're worried about this r is actually the distance from the point of rotation to the actual object. And so for our situation, this is going to be, both of these are times the same angular velocity, right? They both move at the same angular velocity. That's the final angular velocity. And that r, in this case, let's write out the first term, the mass of the rod times the length of the rod plus the mass of the ball times the radius r, which is equal to half, right? In this case, it goes from this point out to the tip. So that's going to equal to L divided by 2. That whole thing needs to be squared. It's not just the L squared, it's L divided by 2 squared, because that's what R is for the ball. Okay? So that's going to give us some information about this is what the final momentum is going to be, and we can figure out what the initial momentum is going to be, given we know the mass of the ball, we know its velocity. The angle here is obviously very important, so we want to make sure that we consider what angle we're using. And it tells us the initial angle is 60 degrees, but we need to know what the angle is for this side of it, on this end, okay? From R cross F, which is the angle from R to F. Or from R to V, I'm sorry, R to V. R cross P. That's what our angular momentum is. Okay? So hopefully that, oops, I'm not sure if that all got into the video or not, but hopefully that's a little bit more clear for helping out with that problem.